So this is question 27 from the chapter 3 homework. And my question says a fair coin is tossed 3 times and the events A and B are defined as below. So event A is that at least one tail is observed, and event B is the number of tails observed is odd. So the way you want to approach a question like this, the way I always approach a question like this, is I draw out a tree diagram so that I can see what are the possibilities for tossing this coin 3 times, what's the sample space for the whole experiment, and then from there I can answer the questions that it asks me to answer. So in our first toss of the coin, you could have heads and tails. Those are the options. And then during the second toss of the coin, you can have heads and tails and heads and tails. And then for the third toss, you can have heads and tails, heads and tails. So in 3 tosses of the coin, if we list our sample spaces, our sample space out to the side, heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So these are the 8 possibilities for tossing a coin 3 times. And so part A asks us to list the sample space for each of the events. And so the sample space for event A is everywhere we have at least one tail observed. So this is 3 heads. There's no tail there, so that one doesn't count. We have 1 tail, 2 tails, 1 tail, 2 tails, 2 tails, and 3 tails. So these 7 possibilities make up the sample space for event A. So I'm going to list those here. Keeping in mind that at least 1 tail means you could have 1 tail, 2 tails, or 3 tails. Then it asks us to do the sample space for event B. And event B is that the number of tails observed is odd. So that means we have 1 tail, 2 tails is an even number, so that one doesn't count. So we have 1 tail here, that's 2 tails. That's 2 tails, and this is 3 tails, and so 3 is also an odd number. So we have HHT, HTH, THH, and TT and T. Okay, so then it asks us to list the sample space in the union of A and B. So when we do the union of A and B, it is basically putting A and B together so that we have everything that's in A and everything that's in B combined into one set. But then we don't list the duplicates. We list everything only one time. And so the union of A and B is going to be everything that's in A. So I'm going to jot those down here. HTT, THH, THT, TTH, TTT. So then it asks us for a complement. And a complement is basically everything that's not in A. So everything, these 7 were in A. The only one not in A was the HHH, the 3 heads. And so that is the A complement. And then it asks us for the intersection of A and B. And so the intersection of A and B is what A and B has in common. So they have an HHT, they have an HTH in common, they have a THH, and they have a TTT. So those four options make up the intersection of A and B. And that takes care of everything that Part A asks for. So Part B asks us for the probability of each of these situations that we just listed the sample space for. So the probability of event A and the probability of event B, the probability of the union of A and B, the probability of a complement, and then the probability of the intersection. So I'm going to do the probabilities just up here beside each of these that we've listed out. There were 8 possibilities, and so our probabilities are going to be some number out of 8. Well, there are 7 in A, so the probability of A is going to be 7 out of 8. There are 4 in B, so the probability is going to be 4 out of 8, and we want to reduce that down to 1/2. There are 7 in the union of A and B, so that's going to be 7 out of 8. There's only 1 in the complement, so that's going to be 1 out of 8. And there's 4 in the intersection, so that's going to be 4 out of 8, or 1/2. Okay, so that takes care of Part B. Part C asks us to do the probability of the union of A and B, but use the additive rule formula to see if we get the same answer as the probability we got of the union of A and B in Part B. So the formula says we take the probability of A, the probability of B, and we subtract off the probability of the intersection because that takes out what they have in common. So the probability of A we had calculated to be 7 over 8. Probability of B we had calculated to be 1/2. But I want to use the 4 over 8 because that keeps us in a common denominator for adding purposes. And the probability of the intersection, again, we calculated to be 1/2, but I want to use 4 over 8. And so when we simplify this, technically you could just cancel out that 4 over 8 minus 4 over 8. Or we could just go straight across 7 over 8 and 4 over 8 is 11 over 8 minus 4 over 8. And that gives us 7 over 8. And so both of those calculations produce the same result. And that is what you would expect. The probability of the union is not going to change depending on which method you use. You should get the same answer both times. And then Part D asks us, are events A and B mutually exclusive, and why? So one of the rules for events to be mutually exclusive is that the intersection would equal 0. They would have nothing in common. So because the intersection of A and B, the probability of the intersection is 4 out of 8, or 1/2, then that means these events are not mutually exclusive. And then what that really means is that A and B can actually both happen. You can have situations where we have at least one tail observed, and that it is also the number of tails observed is odd, because we had 4 situations where we either had 1 tail or 3 tails, which satisfies both of those conditions. So if you have any other questions on this one, please let me know. Please email me, and I would be happy to address those.